All right, I think I'm ready. This is our last little time together. I suppose, I mean, we're gonna have our test on Friday and another test next week, but this is our last regular class. I hope you don't shed a tear. I thought we could all sort of like hold hands around the campfire, but maybe not. We have our test on Friday. I hope everybody knows what to expect. You will see every question on the big list. This will be your last chance, I suppose, unless something's going on. I mean, you can try extra ones next week if you really need to. But that's that for the test on Friday. And then I have made one last homework assignment, which is already posted, which I'm going to make due on on Monday. It's usually Wednesdays, but I'm not supposed to make assignments due after the last day of the semester. So let's say it's due on Monday, although I don't really care if you want to do it on Wednesday. That's fine with me as usual, but I'm not supposed to make things due during the reading days. So anyway, the homework is posted already. I would suggest that you at least take a look at it before Friday. Like, my reason for making the assignment is just so that you will know what kinds of questions I expect you to be able to do about the Taylor series, which is the last topic, which will be on the test on Friday. So you ought to check out the homework before then. And then the final exam, maybe a few words about the final exam. So the final exam will not be based on it's not sort of checklist based. It will be a more traditional exam where you'll have a bunch of questions and I will grade them out of like more points than just 3 points, so you'll be able to get more partial credit. And the final exam will cover potentially anything, although I think just so that to give you like less to have to study about, I'm going to say that the final exam only covers the starred topics on the big list. The deal breakers, but also like including the ones towards the end, which I had originally marked as deal breakers, but then I said, yeah, it doesn't make sense to make them deal breakers. I want to put those on the final exam though. So this would be the Taylor series and the things about Tower series, which had stars on the list. Yeah.
Is it the same question format that we've had on?
Yeah, it should be. You should expect the questions to be similar to the quiz questions. Although I'm not going to, I will just say in some order. So you will not be able to tell what the questions are about per se. Like, I'm not going to say, this is the integration by parts question, and then say, do this integral. So in that sense, it'll be, that's a little bit different from the way that the quizzes have always been. But it will be up to you to decide which tricks or methods to use in each problem. Although I'm not going to try and fool you or anything like that, but that it'll be like that. And I don't actually expect to, I said it'll be about the starred topics, but I don't think I'm actually going to have a question about every one of them. Like, I probably won't just make a U substitution question, because I consider that kind of a review topic anyway, and you should expect to be doing the U substitution as part of one of the other problems anyway. So I'm not just gonna like go down the list and have one for each. There will be probably less than or equal to one question per one of those starred topics. Right. I don't want to make the test super long, although you will have 3 hours. That it's scheduled for 3 hours, and I'll give you the 3 hours. But I'm not going to make it super long. Like, I don't intend for everybody to need the 3 hours, but you can have the 3 hours if you want. All right. Any questions about that? If you do, if questions come up, let me know, and I will be around if you want to get together and talk about things. I would be happy to do that. I won't have my usual office hours just because like class schedules, is over, but I will be around, so just let me know by email, and I would be happy to set up something, get together, and talk about it. All right, great. I hope you're feeling good about the final exam. Okay, for our last day together, I just would like to do a few more examples of the Taylor series. So we did one example last time, and that was of e to the x, right? We did the example of e to the x. When you write it as a sum, it's just this. Or if I were to write it out term by term, is like this. Sorry, I skipped one. X to the 1 first, and then 1 over 2 factorial x squared, and then 1 over 3 factorial x cubed, 1 over 4 factorial x to the 4, etc. All right? The big question in writing power series is always like, how do you figure out what those coefficients are? In this example of e to the x, the coefficients are always 1 over n factorial. But where do those coefficients come from? Well, this is the formula, and I wrote this last time. I will say it again. Maybe I'll say this a little bit more formally. There's a name for this. This is called Taylor's theorem. Taylor's theorem basically tells you how to get those constant coefficients, which in this example, they're all just 1 over whatever factorial. Taylor's theorem, it says, I more or less said this out loud last time, but I didn't write it down. It's a good idea to have this in writing. If f of x is differentiable, it must be differentiable just because this entire method is based on taking the derivative of the function. And so if there is no derivative, then you can't do this at all. If f of x is differentiable, then the power series is, the power series always looks like some constant and then some other constant in front of x, some other constant in front of x squared, some other constant in front of x cubed, etc. That's just what every power series looks like. The real sort of the good stuff of the theorem, what Taylor figured out is this part where, how do you figure out what those constants are? This is how. This is Taylor's big discovery. Those constant coefficients always have this format. So that thing in the box is the important thing. It tells you how to find the individual constant coefficients in the power series. I think I wrote this last time, but this is called Taylor's theorem. Now, the way that I've written it here is for a series centered at 0. Remember, you can also do the series centered at A. And Taylor covered that also. So here's part 2. This, what I'm about to say, I didn't say last time. For a series centered at some other value, A, it's, first of all, the way you write such a series is, the same idea, constants, but instead of powers of x, you have powers of x minus A. Etc. So for a series centered at A, you write the series like this. And then, what are the constants? Taylor worked this out also. This is another formula to remember, although it's pretty simple. It's just, instead of plugging in 0 every time, you plug this other number A every time. All right. And there's some special terminology, which I don't usually use these words, but when you do the assignment in the book, you will see they use these words all the time. When it's centered at 0, it's called it has this other guy's name on it, Maclaurin series. And these ones, just any center, this is called the Taylor series. So when you see in our book there are problems, find the series of whatever. When they say find the Maclaurin series, they mean centered at 0, where the terms all just have some power of x. When they say find the Taylor series centered at whatever, they mean do this. All right. Now the Maclaurin series is also sometimes called the Taylor series. Like in general, all of this stuff is called the Taylor series. And I will usually just call them all the Taylor series, either centered at 0 or not. But when you see Maclaurin series, that means specifically the Taylor series centered at 0. All right. So all I want to do today really is just a couple more examples like this. Last time we did e to the x as an example. Let's try. Really, you could do this, work out the power series for any of your favorite functions. Let's try sine of x. So this, if it were a homework problem, would say something like find the Maclaurin series for f of x equals sine of x. All right? What this involves is you have to basically do this, which the hard part of this is figuring out what those derivatives are. So let's find the various derivatives. And this is what we did last time for e to the x. Maybe I'll start down here. For e to the x, this was very easy because it involves taking the derivative over and over again. But for e to the x, the derivative over and over again is just e to the x every time. For sine of x, it's not so simple, but it's not so complicated either. Can you take the derivative over and over again of sine of x? I think you can. The derivative of sine, of course, is cosine. Everybody knows the derivative of cosine. So the second derivative, the derivative of cosine, is negative sine x. If I take the derivative once again, derivative of negative sine would be negative cosine. Somebody asked me earlier today, how far do you got to go with this? The answer is you should keep doing this until you see what the pattern is, basically. All right. I'm not sure I see a pattern exactly. What's the derivative of minus cosine? The derivative of cosine is negative sine, so the derivative of negative cosine will be positive sine. So this, the fourth derivative, is positive sine x. The fifth derivative is cosine x. Anybody see a pattern here? It's not really easy to say in words what the pattern is, but actually I feel like I have sort of sunk into a loop here, right? I have those four things. It goes sine, cosine, minus cosine. And then it's back to sine, and beyond that, it's just going to do the same thing again, right? It'll be sine, cosine, minus cosine. So this sort of four block pattern will just repeat itself over and over again. All right, that's the pattern. I don't know if I can say that in any fancier terms than that, but this is the pattern. You have these four things, and in blocks of four, it's going to do that forever. All right. So anyway, these are the derivatives. Now, since I'm doing the Maclaurin series, I want these things. I want the derivative with 0 plugged in. So for the Maclaurin series, we are going to plug in 0. The first one is f of 0, then it's going to be f prime of 0, f double prime of 0, etc., right? So for f of 0, I hope you all remember your sine and cosine of 0. Sine of 0 is 0, cosine of 0 is 1, right? So for f of 0, I get sine of 0, which is 0. F prime of 0, I get cosine of 0, which is 1. F double prime of 0, it'll say negative sine of 0. That's 0, because sine of 0 is 0. The fourth derivative, this will say negative cosine 0. That's negative 1. And then, just like before, this sort of block of 4 will repeat forever. So the pattern is it goes 0, then 1, 0, then minus 1. And then it repeats 0, 1, 0, minus 1. So the terms here go 0, 1, 0, minus 1, etc. forever. Sorry, I kind of ran out of room there. I guess I could scroll. We have the scrolling technology, right? 0, 1, 0, minus 1, etc. forever. All right, those are the coefficients. Okay, so we have now enough information to write the Taylor series. Remember, the coefficients each time, they look like 1 over n factorial times this derivative part. So the coefficients I use will be these numbers, and each time it will be times those factorials. So I can say sine of x, remember it looks like c0 plus c1x, c2x squared, c3x cubed. Maybe I'll just write that much. What are those constants? They come from these derivatives times a 1 over whatever factorial. But anyway, the very first one, for sine of x, the very first one is a 0. So actually this term is just going to be a 0, 0. The next one is a 1. So the next term, the coefficient part, is 1 times x. So this is just plus 1x plus. Now these ones we also need to include the factorials. So this will have 1 over 2 factorial. Every Taylor series always has the factorial part. And then you insert the constant that we just calculated. C2 will be the second derivative, which is 0. So this is a 1 over 2 factorial, 0x squared. Next, 1 over 3 factorial. The third derivative. What did I write here? Sorry, did anyone notice? I wrote this. This is supposed to be the third derivative. I just skipped over. I went from second to fourth. I don't know why. This is the third. The next one is the fourth. Sorry about that. This is the third. The next one is the fourth. I don't know what happened in my brains. This is my last class to teach of the semester. I got to go out strong. I'm flopping here. All right. So anyway, right here, I want to see the third derivative, which is -1. And then x to the cubed. All right. Can you see the pattern here? What the pattern is all the evens have zeros in front of them. So actually these won't be in there at all. Like if we simplify here, we can just skip all the even terms. And the odds all have either 1s or -1s. So this is etc. But if I were to just sort of clean this up, all it is you get only the odd powers of x, right? And they are going to alternate in signs because of the pattern of the 1s and the -1s, right? So the next will be a plus 1 over 5 factorial x to the 5. The next will be a minus 1 over 7 factorial x to the 7, and so on. This is the pattern here. We see only the odd powers. That's because when you take those derivatives, all the even derivatives are 0. Only the odd powers. They alternate in signs. It's because these derivatives were alternating. I got 1s and then -1s and then 1s and then -1s. All right? This is sort of my final answer. This is the Maclaurin series. You can put that in your box of series that you have been keeping somewhere in your notes. This is the series for sine of x. All right. This one, I want you guys to try cosine, but I have one more thing to say about this one, and that is, let's try and write this as a summation. This is actually slightly tricky to write as a sum. Usually I like to write, something times x to the n, right? This is ideally how this is going to look. But what's hard about this one is actually like many of the x to the n's don't appear at all here, like x squared, x to the 4, the even ones just aren't there at all. So actually it's not possible to write this as a nice formula in this way with just x to the n. Instead, we see here only odd exponents, and the trick to make that happen, this is a little non-obvious, but once you see it once, this is how you make it happen, that the exponent will always be odd. So this, whatever the n is, I do 2n plus 1, that forces the exponent to only be odd numbers. The first one will be, when n is 0, this is a 1 power, which is power of 1. When n is 1, this is a third power, which is what we want. And then we also need alternating the signs. This is how we alternate the signs. And we also need the factorial part. And this is a little weird looking, but what goes inside the factorial has to match the exponent, right? Exponent of 5 goes with a factorial of 5. So whatever, this exponent, 2n plus 1, needs to be the same factorial on the bottom. This is kind of complicated looking, but that is the Taylor series for sine of x. All right. All right, anyway, I would like you to try all the same stuff for cosine. It will be very similar, but you should start by taking these derivatives, right? It's very similar, but everything is slightly different. See what you get for the series here. I'm going to try and scroll this out so you can see everything at once. Starting with cosine, you should be able to get something. Your series will look kind of like that, but a little different. send me emails. Send me emails. I'll check it out. You don't have to worry about it. All right. Yes.
Yeah, and from minus.
Oh, okay.
Yeah.
That wasn't big enough. Great. Can you write as a? Yeah, so the reason this says 2n plus 1 is because I want them to be odd all the time. So the 2n part would be even, and then you add 1 more. But you want it to be even all the time? I would say just 2n, because that's even. People seem to be doing all right. If you work out the derivatives, I think everybody got this far at least. That's the pattern of the derivatives. And so when we build the series out of this, it's pretty much the same as that, only you don't like in the sine you get all the odds, but in the cosine you just get all the evens. Otherwise it's kind of the same thing. So this gives, and I think as I was going around, I think everybody came up with this, so maybe we don't need to work out all the steps. You get 1 first, and then minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4 minus 1 over 6 factorial x to the 6, etc., like that. This is the series for cosine. I don't know about you, I find it very, very satisfying. There's something kind of, would you mind me using the B word? There's something kind of beautiful about these formulas and how they are so similar to one another, but just kind of like a little bit different. This is like how I would describe, you know, if some kid asked me, hey, what's the difference between sine and cosine? I would say something like, well, they're kind of the same, it's just like one is a little different from the other one. Like you use them both to do the same sorts of stuff, they're just a little bit different from one another. And from this point of view, I feel pretty good about this. Like it's pleasing to me that the sine and the cosine are written in this way. The sine has only the odd powers, the cosine has only the even powers. I think there's something cute about that. If I were to write this in the summation format, it would look like, okay, we do have alternating signs, so we need to put minus 1 to the end. That's always how you alternate the signs. And then it looks just like the one for the sine, which you can still see up there, only instead of odds every time, I want evens every time. To make this always even, you should just use 2n without the plus 1. That's going to be even every time. So it should look like that. That's the summation format of the formula for cosine. All right. So I would like to, if you don't mind me waxing a little bit even more about this. This is the series for e to the x, which I hope you have written down somewhere. That's the series for e to the x. Sine of x looks like only the odd ones. Sorry, I shouldn't have written the 1 there. Only the odd ones. X minus 1/3 x cubed. The next one will be plus 1 over, not 1/3, 1 over 3 factorial. There's factorials there, right? And then the cosine one is only the even ones, including sort of like the 0 one. And this should be a minus here, sorry. I'm just copying what I wrote a moment ago. I'm writing them all next to each other because I'm trying to make a point here. All right, sine of x has only the odd ones, cosine has only the even ones, e to the x has all of them, all right? This is another thing that is unexpectedly beautiful in my opinion. I can remember my mind was blown as a young lad when I first learned about this. It seems to me, looking at these, the cosine has only the even ones, the sine has only the odd ones, the e has all of them. It seems to me that I feel like maybe you should be able to like add these two up and get that one somehow, because they sort of like fill in the blanks of each other, and you would get, if you added these two together, you would get all of the terms, and they always look like 1 over something factorial times x to some power, all right? So this is a question, when you see all of these together, you begin to ask a question which actually, like, to a high schooler, this sounds like the stupidest idea ever. But when you look at this, you ask yourself, is there some way I could add together sine and cosine and get e to the x? I would say, if a kid asked me this question, the correct answer is, no, you idiot. Sine and cosine have nothing to do with e to the x. There is no reason why you should think, like, if you even thought that, it's because you're insane. Like, there's no reason why adding up sine and cosine should ever have anything to do with e to the x, because they are completely different things, which, in fact, like in the history of humanity, they were invented by very different people, separated by many centuries for completely different purposes. But actually, someone who suggests this is not being an idiot. There is, I mean, it looks to me like maybe you could add those up and get the other one. Now, they don't just literally add up to get the other one because of the signs, right? These have alternations of the signs, pluses and minuses, and this one is all pluses. So if you just straight up add these two together, you don't get that one because the signs are messed up, all right? But actually, somebody figured out, this is something that Euler, this is a famous European guy, discovered, that if you add them up in this way, if you plug in, instead of x, you plug in ix. where I is the square root of -1. This is an imaginary number, which I'm sure you've heard of. Think about what the effect is if instead of x you use ix. Remember I, the whole point of I is when you square it you get a negative, all right? If you plug all of these x's, instead of x's you use I times x. This one, when you square it, it becomes negative. Then the sign actually will match this the way you want it, all right? If this one, when you take the third power, it also will become negative. If you do I squared, you get -1. That means if you do I cubed, you actually get minus I. And it anyway also becomes negative. It turns out, if you insert the I here, it's just right to make the signs flip-flop in exactly this way. And this is actually a true fact. Sorry, what you get specifically is cosine x plus I times sine of x. This is actually not hard to work out the details if you are interested. You can just plug in e to the ix in the first formula and see what happens. You'll be able to simplify it, and you will see it actually does equal the cosine of x plus I times the sine of x. All the signs work out properly to make this true. This is a super interesting and completely unexpected formula. This is the kind of thing, if somebody asks you, is there some relationship between sine and cosine and e to the x? The simple answer is no, there's not a relationship. But actually, yes, there is. This is not something that anybody expected to be true, but it really is true. Something really interesting about this is, and this is Euler realized, if you plug in, check this out, x equals pi, what do you get? On the left side, you get e to the power I times pi, whatever that is. And on the right side, you get cosine of pi, actually we can simplify that, plus I times sine of pi. And we can simplify that too. Cosine of pi, I hope you remember from your trigonometry, cosine of pi is -1 and sine of pi is 0. So this actually says e to the I times pi equals -1. This is truly profound. Sometimes this is also written, if you add 1 on both sides, it's written this way. This right here, this is referred to as Euler's formula. And this is sort of most mathematician, if you ask them like, what's the most beautiful equation in the history of mathematics? This is like the standard answer to that question. I'm not saying everybody thinks it's the most beautiful formula, but this is usually what is typically called it's like if you ask someone what's the greatest classic rock and roll band, they say the Beatles. That's like the default answer. Now there may be other answers that are valid, but this is the usual answer for the most beautiful mathematical formula ever. This is because like what we have here are 5 different numbers, and they are in some sense like the most important numbers in all of mathematics. Like if you just ask someone in the club, like what are the 5 most important numbers? I would say, to me, like I gotta go with 0 and 1. Those are like the OG numbers, right? 0 and 1, you can get all the other numbers by adding those together. And then, if I want to do geometry, I gotta take pi, of course. If I want to do calculus, I gotta take e. And if you want to do some kind of fancy algebra, you have to use I. So those are the 5 fundamental numbers, which are the most important numbers in all of mathematics. And what's interesting about this is that they all actually sort of come together in this way, which is completely unexpected. These numbers were created in different times and places. Like the number 1 has kind of always existed in human societies. The number 0 came along maybe like 1,000 years ago or something, like in India, people came up with the idea of the number 0. And then pi comes from like the ancient Greeks. E comes from sort of like European capitalists doing compound interest calculations. And then I comes from sort of far out abstract mathematics. But anyway, these numbers were all invented to do different purposes, but they all come together in this one way, which none of the people who created any of these things expected that this would be true. So this is widely viewed as a remarkable fact. This is the kind of thing that like there are lots of you can Google for math tattoos of this. Lots of people have this tattoo. I'm not a tattoo guy, but I don't like when I look for pictures of. I don't often do this, but when you search on Google for pictures of tattoos, you get like people who, I guess they're like really proud of their new tattoo. It's always like a new tattoo that's got like little bloody bits all around it. Like, just wait a week or so before posting your new tattoo. This is my advice for the internet. But anyway, this is a popular math tattoo. If you want a fairly sophisticated but not too complicated math tattoo, this would be a good place to go for it. I just thought I'd share this with you. Anyway, we got 15 minutes remaining. Can we just I want to do 2 more examples, and then that'll do it for us. Euler's formula, super interesting. It seems ridiculous that this could be true, but it actually is, and it's not so hard to prove that using this series. Okay, can we do 2 more examples? Let's try an example of a function where it doesn't have such an obvious pattern. I would like to do e to the 2x, and I want to find the Maclaurin series. All right, we're going to do this just like we did for sine and cosine. It involves taking the derivatives over and over again and trying to figure out what the pattern is. Now for sine and cosine, the pattern was like 1, 0, minus 1, 0, and so on. For this one, it's going to be different. We just have to figure it out. But anyway, it begins by taking, so my original function is what we start with, and then we take the first derivative and the second derivative and so on. Anybody want to say, this is not a trick question, what's the first derivative of e to the 2x? Somebody want to shout it out? On our last day together, surely you can feel free to participate. Yes.
Is it 2 times e to the 2x?
Yes, thank you. I appreciate your participation. Yeah, 2 times e to the 2x, right? Derivative of e to the 2x, you just get the same thing again, e to the 2x, but then because you are doing the chain rule, you got to multiply by 2. So 2 e to the 2x, great. What about the next one? Take the derivative again. I think when I take the derivative again, I got to do the chain rule again, and I'm going to get another 2, which will sort of come out of the exponent and multiply onto the front. This now becomes 4 e to the 2x. This 4 comes from multiplying another 2 because of the chain rule. All right? Okay, do we see the pattern yet? I don't know. We're trying, like I said before, do enough of these so that you can tell what the pattern is. The next one, I take the derivative again. I get another factor of 2 in front, which multiplies the 4 and gives me 8. So the next one will be 8 e to the 2x, and so on. Can we say generally, f, the nth derivative of x? Can anybody see the pattern here and say it in terms of n? I mean, every time it's clear to me it's something times e to the 2x. What exactly is that something in terms of n? This is the n equals 1 here, n equals 2. What do you think? Yes.
Is it 2 to the n?
It's 2 to the n. Thank you. Thank you, Nick. Maybe it's better if I say your name out loud. Yeah, it's 2 to the n. 8 is 2 to the 3, right? That's where that 8 comes from. So 2 to the n, e to the 2x, right? This is the general pattern for the nth derivative of x. All right? So in order to find the series, we have to plug in 0. But actually, rather than writing the big list of what I get when I plug in 0, I can just directly plug it into that, right? So f, the nth derivative at 0 would be 2 to the n, e to the 2 times 0. I'm plugging in x equals 0. E to the 2 times 0 would be e to the 0, which is just 1. So this is just 2 to the n. All right? It means when I write my series, in addition to the factorial thing, I also am going to see 2 to the n every time. So the series, well, we can just write it. Given what we've done so far, it's actually easier to just write it as a summation. It would be the sum. 1 over n factorial is what you always get, and then times 2 to the n, x to the n. All right? This 2 to the n is what goes right here. So this is the series written as a summation. If you want to write it out term by term, that's fine. The n equals 0 term would be 2 to the 0, which is just 1. The n equals 1 term would be 2 x to the 1, and then I would get 1 over 2 factorial 2 squared x squared, 1 over 3 factorial 2 to the 3 x to the 3, and so on. That's the series term by term. All right. So sometimes you got to do a little bit of work, and then in the ones on the homework or what you should expect to see on the quiz will involve do a few of these, and then you may have to figure out some simple pattern. Here, I hope that all of you could see this, even though you weren't saying anything. The pattern here is you are getting powers of 2 each time. So that's the pattern, which you eventually fill into the series. All right. One thing that we haven't talked about, I don't know if we need to go through it. Well, I don't think we need to go through an example, but I would just say you can, if you want, and on the homework, they're going to ask you to do this for some of them, you can find the interval of convergence and the radius of convergence if you prefer, as usual, using the ratio test, right? What we have here is just a power series, and so we already know how to find the interval of convergence for any power series by using the ratio test. So if you like, after finding the Taylor series or whatever, you can also find the convergence interval. All right, I got one more. One more because we haven't yet done any examples of this other type, right? So all of the ones we've done so far have been Maclaurin series, that is using just powers of x and plugging in 0 every time. But instead, we can do these other types, which are centered at another value. Let's just try one of those and see what happens. Let's try find the Taylor series for sine of x centered at a equals pi over 2. All right. We already did sine of x centered at 0. This is centered at pi over 2. What's the difference for the centered business? The difference is we're going to use x minus a to the power n instead of just x to the power n, and we use the nth derivative evaluated at a instead of the nth derivative evaluated at 0. But otherwise it's the same. So we are still going to find all the derivatives, but then we plug in, instead of plugging in 0, we're going to plug in a, which in our case is pi over 2. And then when we write our answer, the series terms, they don't say x to the n, they say x minus a to the n. Anyway, let's do it. So this, I have, first of all, our derivatives. Now these really are exactly the same as when we did this example the first time. So it's the same sort of repeating pattern of derivatives. The second derivative is negative sine. The third derivative is negative cosine. And then the fourth derivative, we sort of loop around and we get sine again. So this is the pattern which repeats in blocks of 4. All right. Next, I'm going to plug in, but I'm not going to plug in 0 this time. I'm going to plug in a equals pi over 2. So I do f of pi over 2. I hope everybody remembers our pi over 2's. Maybe I'll draw the graphs of sine looks like that, and cosine looks like that. So sine of pi over 2 is 1. Cosine of pi over 2 is 0. So that's what we're going to get when we plug these all in. This is sine of pi over 2, which is 1. I just said 1, right? F prime of pi over 2, this would be cosine pi over 2, which is 0. F double prime pi over 2, that's sine, it's negative sine of pi over 2, that would be negative 1. And then the third derivative at pi over 2 is negative cosine pi over 2, but that's 0. So this is our pattern here, 1, 0, minus 1, 0, etc. Right? Those are the coefficients this time around. All right, and I think we can just write out. So you can see here, actually, when I write the series this time, I'm getting only even only the even terms, right? The second, I do not get the first term, it's 0. The third term is 0. I get the second, this is sort of like the term 0. I'm gonna get the fourth term here. So anyway, it'll say sine of x is, we begin with 1 as the constant term, 1. There's no x to the 1 term because the next coefficient is a 0. There is a x squared term, and I have a minus. So actually, I shouldn't have written 1 plus. I should have said 1 minus. As always, we need the factorial part, and then x minus pi over 2 squared, right? Ordinarily, we would say x squared, but I'm doing centered at pi over 2, so it's x minus pi over 2 squared. All right. Next, the degree 3 term is a 0 because the third derivative is a 0. That's right here. The degree 4 term is a plus 1, so I go plus 1 over 4 factorial x minus pi over 2 to the 4, right? The next term will be, the degree 5 is a 0. The degree 6 is a minus, according to the pattern up there. Maybe I'll just put my dot, dot, dot after this. Like so. This is the Taylor series for sine of x centered at pi over 2 rather than centered at 0. All right. I think that's all I got. I hope you're feeling good about these. My suggestion is that you try to do the homework right away. I mean, you don't have to actually write it up and hand it in, but at least look at the problems and make sure you could do them, because that's what you should expect to see on the test on Friday.